This lesson introduces the trapezium rule as a method for approximating the area under a curve. We'll start with this example. The curve is y equals 3 root x, and we want to find the area bound by the curve, the lines x equals 1, x equals 4, and the x-axis. So you can see the 2 points of intersection there, 1, 3 and 4, 6, found by substituting the values of 1 and 4 into 3 root x. Now, to approximate this area, I'm going to connect those 2 points with a straight line, thus creating a trapezium. To find the area of the trapezium, we use the formula half a plus bh, where a and b are the 2 parallel sides, which are vertical in this case, and h is the distance between the 2 parallel sides. Substituting in the values gives us a half of 3 plus 6 multiplied by 3, resulting in the area of the trapezium, 13.5 square units. Now the trapezium sits under the curve, and so this is an underestimate for the area that would be enclosed by the curve. But we can improve on this estimate by using a few more trapeziums. You can see I've plotted a few more points here by substituting x values 1, 2, 3 and 4. So we've got 4 points creating 3 trapeziums. Those points are sometimes called ordinates. So we've got 4 ordinates and 3 trapeziums or strips of area. The first trapezium, we substitute in the values of 3 and 3 root 2 for the parallel sides, and the distance between the parallel sides is 1. So the first trapezium has an area of approximately 3.62 square units. Repeating that process for the second and third trapeziums gives us a total area of 13.9 square units. Now you can imagine that if we had several more trapeziums, calculating the area of each one individually could become tedious. So we can combine into one calculation, because each of these 3 has a factor of a half and 1 for the width of the trapezium. And then we've got 3 and 6, which are the first and the last y values. 2 lots of 3 root 2, which is the second y value. 2 lots of 3 root 3, the third y value. And so the trapezium rule is sometimes summarised as half a width of the strip multiplied by the first plus the last plus twice all the others. And notice that this is still an underestimate because all of the trapeziums fit under the curve. So our first estimate with 1 trapezium gave us an area of 13.5. This one with 3 trapeziums gives us an area of 13.9, both of which are underestimates for the actual area under the curve. So you can probably predict the exact area under the curve. And if you've studied definite integration, you will know how to calculate this. Please pause the video now and calculate the definite integral to give an exact value for the area before you watch my solution. Firstly, we can simplify by writing the square root as x to the power of a half. Then to integrate, we raise the power by 1 and divide by the new power, and notice the square brackets and the position of the 4 and the 1. We can simplify this and then substitute in those values of 4 and 1 to give a final answer of 14 square units, which confirms our approximations of 13.5 and 13.9 were underestimates for the exact area under the curve. Now the trapezium rule really comes into its own when we're unable to integrate in that way. So here's a new function, y equals 1 over 1 plus x cubed, and I want to find the area bound by the curve. The lines x is negative 0.6, positive 0.6, and the x-axis. If we know how to integrate this function, then we can use this method. Otherwise, we can approximate by drawing straight lines to create trapeziums on the curve. we now need some coordinates or ordinates, and so we substitute in the values of negative 0.6, 0 and positive 0.6 to give us the three y values, or the lengths of the parallel sides of those trapeziums. So to approximate this definite integral, we've got the first trapezium on the left, which is a half, the sum of the parallel sides and the distance between the parallel sides, and then the second trapezium on the right, a half, the sum of the two parallel sides multiplied by the distance between them, or combining into one calculation, a half multiplied by the width of the interval, and then the first, the last, and double the middle y value, giving us an approximate area of 1.23 units squared. Now notice in this case that the trapezium on the left is actually an overestimate of the area, and the trapezium on the right gives an underestimate of the area. And so this approximation we can assume is fairly accurate, since part of the calculation gave an overestimate and part of the calculation gave an underestimate. This would be more accurate than if both trapeziums were under or both trapeziums were over the curve.